This video is about the application of sensors in autonomous. So first we will be going over the encoder, the built-in encoder functions in VEX code. Second, we'll be discussing how to write a PI controller. So what we will be going over within this is how to multitask and how to tune it. Lastly, we'll be discussing straight encode for your chassis. If you've seen the video Intro to Autonomous, in that video we cover the first type of autonomous here. This video today will cover the other two types. The second type of autonomous code, which is the encoder-based auton using the built-in spin functions, it's a lot more consistent than the timed autons. Also, given for how simple it is to write and how much better it is than timed autons, if you are a beginner team, I would actually always recommend going for this type of auton over here. However, if you are a more advanced team, I would encourage that you write a custom controller. One big advantage of a custom controller is that you can account for physical factors that may throw off your robot. And then after you account for those physical factors, you can correct them accordingly so that the robot is able to move in the same fashion every single time. So in this box over here, this is the built-in encoder spin function. So what you would type out is the motor name or the motor that you want to rotate, then afterwards dot rotate to, and then you would fill in the parameters accordingly. So the first parameter over here is rotation. You would enter in the absolute encoder degree that you want the motor to go to. Next we have the rotation units. So the most common one is degrees, and there's no need to use anything else. Degrees will fit in all scenarios, so that is why I'm not going over the other ones. Next we have velocity. This determines how fast the robot will move while it is trying to get to that encoder count. Generally, lower velocities are preferable since they are more accurate. Next we have the velocity units. They can be either voltage, percent, or RPM. And finally, we have a blocking boolean. So if this is true, what that means is that this line will be blocking. The code will not move on until the encoder count is met. However, if this is false, the code will just move on normally and the next line will be read. We'll get to that last part in a bit. So this slide over here has example code that uses the rotate to spin functions. In the beginning over here, we are declaring 3 motors. There are 2 motors over here for the drive, and then there is 1 lift motor. In autonomous 1 over here, what's happening is that we're moving the right drive motor at 1000 units, then the left drive motor, and then we're spinning the lift. I want you to pay special attention to the falses over here. How exactly this will be read by the code is that, okay, so the code will check if this is blocking. Since it's false over here, this line is non-blocking. What that means is that the next line will be read immediately afterwards. Alright, so now this line. Over here, this line as well is non-blocking. What that means is that the code will just read the next line as well. All 3 lines will all be read instantly after each other. And what that means for the autonomous is that the drive will start moving at the same time as the lift. Everything will happen in conjunction over here. As for autonomous 2 over here, things are a little bit different. Over here we have a false, but then we have a true. So the thing with this is that the first line over here, it's non-blocking. That means the next line after will be read. But this line over here is blocking. What that means is that until this left drive motor reaches 1000 units, the lift won't start spinning. In other words, the chassis will first have to move, stop, and then afterwards the lift will start spinning. Always make sure you're giving special care to the booleans over here, and the reason for this is because sometimes there could be unintended behavior. For example, if this were a true instead of a false, what would happen is that first the right side would start moving, and then the left side would start moving after the right side stops moving. That means the chassis won't be going forward, and the motion won't be really what we want probably. with this, always make sure that you're paying attention to exactly where you are putting the truths within the code. Before getting into how to write custom controllers, we first need to cover something called multitasking. Alright, so let's look at this code over here. In this main function over here, we have a while loop, and then we are printing something. But there is an issue with this piece of code. The code will get stuck at this while loop over here. In fact, the hello world won't even be printed. In other words, the while loop over here becomes problematic because the code will just get stuck at this while loop. Alright, but what if we wanted to have two while loops running at the same time without them getting stuck? Is that possible? Well, yes, that is possible. And that is what multitasking is about. So here's a better example of why tasks are useful. So let's say in our autonomous we wanted this function over here, called function. Let's say this function ran calculations for something that we want during autonomous. Let's say it was continuously running, so that means we want that the function has a while loop inside of it. If we wanted that function to run in the background of autonomous, that'd be really, really helpful for autonomous. So how exactly do we get that to run in the background? Well, this is the syntax you would use. You would type in vex. So this is the vex namespace, then double colons, task, then space, the instance of the task, and then in parentheses the function you're referring back to. So this is something that will allow this function over here, this while loop, to run in the background pretty much, all while the stuff after will run normally. Like for example, if we had a while loop instead of this line over here, what will happen is that autonomous will get stuck. It will get stuck at that while loop. Everything that happens past that while loop will not run. However, because we have a task over here, what the code will do, it will just read this task, then have the while loop run in the background. Then while the while loop is running in the background, everything afterwards happens normally. To stop the task that you created, you would type in the instance of the task, then afterwards you would do dot, and then stop. That will terminate the function in the background. Now, since we're done talking about multitasking, we can actually get onto how to write the PI controller. So overall, this is how the PI controller works. Let's say we have this, I guess, rectangular robot over here, and it moves in a straight line, just like your robot probably does during autonomous. Let's just say during autonomous, we want the robot to go to here, and it starts off at this area. How the PI controller works is that it takes feedback, and then it processes that feedback, and then assigns a power to the motors on the drive in order to get to that point. More specifically, that feedback is how far you are from this point. So that feedback over here would be this green bar. Is that there's two components to the PI controller. There's the P component, which is the first one, and the I component, the second one. While this overall explanation might have been vague, we'll actually go into more specifics when talking about the P and then the I. We're going to begin, of course, first with the P. So let's first begin with the P controller. So the expression for the P controller, or the P power, is this. P power is equal to Kp times error. So we just introduced two terms here that are new. We introduced one Kp and second error. So what's Kp? Kp is a constant that you're going to be tuning so that the PID best fits the system that you're using the PID for. For this example, we will be setting Kp equal to 10. Alright, now the error. The error is pretty much equal to the distance between where your robot is and where it wants to be. So let's just say that you have an integer or a variable called target, and this is how far you want to go or where you want to be. And currently your position, you can calculate that, is just your motor encoder. That will be equal to the motor dot rotation. So in other words, this green line over here, that's equal to error. This is just visually represented. To get the actual expression for error, this is what it is. You would take the target, then you would minus where you are at. So you're pretty much getting displacement. So error is equal to target minus where you are, or the motor rotation, or the encoder rotation. So how this works exactly and what it means for the robot is that initially the distance between where you want to be and where you are at is really, really high. Like let's say, for example, the target's equal to 1000 and you're currently at 0. What this means is that initially the millivolt power is going to be 10,000. But then what happens as you slow down? Or what happens as you get closer and closer to the target? What will then happen is that, okay, you move forward, like over here, and then your error gets smaller. This distance becomes smaller. And since the power is dependent on the distance, it's proportionally equal to the distance, that means that the power that's assigned will get smaller. In other words, as you move towards the target, your robot will slow down and just keep on slowing down until it reaches a stop smoothly. This is really different from a time autonomous, in which for the time autonomous you're just going at a certain speed and then you're abruptly cutting off that speed. Here on the other hand, you're slowing down and gradually easing into the target. So that's pretty much all there is for the P controller, and now we can move on to the I controller. Now there's one issue with the P component, or the P controller, that the I controller addresses. So let's go back to the scenario in which you're just moving using the P controller. You're going to keep on moving, your robot's like going to keep on moving. But then as you get closer and closer, remember, the error becomes smaller and smaller. What that means is that the power assigned is smaller and smaller because the power is dependent on the error. So what that actually means is that as the robot keeps on going, eventually it's going to reach a point in which the error is super small. And that means that the power is really, really small as well. And then if the power is really, really small as well, like if the power is, for example, or let's just say the error is, for example, 40 units, what the millivolts is, that's just 400. That's a really small number, and like the robot may not even move depending on the weight of your robot. So that may be an issue. The reason that this is an issue because the robot's only going to keep on slowing down. As it gets to the 40, for example, it'll just like be very, very slow. And then it might not even make the target, and chances are it won't. That's why you need the I component. The I component pretty much fixes this by providing a little bit boost to the robot at the end, so that when it's moving kind of slow over here, it can just give it some more speed, so that it's able to reach the target. This is exactly the expression for, or let me write down the expression for the I controller over here. So the I power is equal to Ki times integral. So we also just once again introduce two more terms. You first introduce Ki and then integral. Ki is pretty much a constant like Kp. Generally this constant is tenfold smaller than the Kp, and the reason for this is because, well, you'll see in a bit. So then, for example, an appropriate one would be around 0.01 in this instance, if the Kp is like 10, for example. Alright, so the Ki is just a constant. So now what about the integral? What does that mean? Yeah, what even does that mean? Well, the integral is just a fancy way of saying the continuous sum. So how exactly that works is that this is the expression of it. The integral is equal to the previous integral plus the error. In other words, you're just continuously summing the error, and that's equal to the integral. So what does this mean? As the robot gets closer and closer, like let's just redraw the robot here. As it gets closer and closer, and let's just say this is the target, it's eventually going to slow down. But then if we're able to provide the I, let's just say the I component kicks into action right here when it's just starting to become really, really slow. What will happen is that the I will accumulate very, very quickly. And why, you may ask? Because let's say this area is 40. Well then, since the integral is just the sum of the error, that will be equal to 40. Okay, then the next time around, it will be equal to 40 plus 40. Then the next time around, when we move a little bit forward, it will be 80 plus the new error, and so forth. So as you can see, it accumulates really steeply. This is what it looks like on a graph. Just accumulates very, very, very sharply. This is time, it's the integral. Alright. So in other words, since the integral accumulates super sharply and you're giving the motors this I power, you're pretty much giving it a boost. You're giving it a boost that the P controller just can't provide. That's why the I controller is super necessary for small, accurate movements. Alright, so then you might be wondering, well, why are we starting the I component like when it's becoming, like over here for example? Why are we starting the I component when the robot's already super close to the target? Well, let's just go back to how the I component works. It accumulates very, 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 very quickly. What this means is that, like, for example, if the error is 1000 over here, it's going to eventually be 1000 and then plus some absurd number like 900, and then it will be 1900 plus another very large number, and then so on. Then yeah, it'll just be a very, very large number, and there'll be way too much power assigned to the motor. Like, chances are, since you're going to be running this inside a while loop inside a task, the I power is going to be way too much. That's why you need to only run the I power when the robot it's very, very close and when it needs it. Otherwise, the robot's just going to overshoot. So how exactly do we get, I guess you could say, the bounds or the integral to accumulate only within the bounds that we specified? So over here, let's just introduce a new term. Let's call this point at which we want the I to start. Let's call that equal to the integral bound. The integral bound. That's an underscore, by the way. Alright, so here's the expression. Or actually, let's just derive the expression. Why not? So if we want pretty much the integral to start accumulating anywhere from 40 to negative 40 of this target, well, these purple bars, they're pretty much error, right? They're equal to error. So what essentially we're saying is that the error must be between this. The error must be less than 40 but greater than negative 40. So then we can actually represent this condition or these bounds using the absolute value function. So as long as the absolute value of the error is less than the integral bound, which is 40 over here, we want this I to start accumulating. So pretty much we're going to be then having the expression, okay, these are semicolons. So then only when these conditions are met, we want the integral to start accumulating. So we want the integral is equal to integral blah 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 plus error. However, if it's not within those bounds, well, we don't want it to accumulate. We just want it to be equal to 0. So then after this if statement, we're going to have an else integral is equal to 0. That's pretty much all there is to know for the I component as well. And then before talking about tuning, we're just going to be organizing whatever we learned. So now let's just condense whatever we learned and make sense of it so that we can actually write code. Alright, so let's begin with the P power. We know that the P power is equal to, like it says over here, Kp times error. Well, the thing is, we actually haven't said what the error is equal to inside our code. So let me just real quickly set up the function, float PID calc. Then you want your sensor to be your input. So it's like this. Well, the target, you're going to be modifying within autonomous, so let's just have that as a global variable. So here, this is in target is equal to, I'm just initializing it first. Great. And then now, since we have everything that we need to write the error, the expression for error, which is equal to the target minus where we are, or the sensor, we can have int error is equal to, where did it go? Target minus sensor. Alright, great. Also, now we can just write the expression for P power over here. So we know P power is equal to Kp times error. So we can just simply do int p power is equal to kp times error. Well, oh, I actually forgot to define the constants. So kp and ki over here. All right, great. So now we're done with the p component. Now we need to move on to the I component. So as talked about over here, right here, this is the I component. The I power is equal to ki times integral. Well, we actually haven't defined integral, so we need to write an expression for integral. In order to do that, we're just going to look back here, whatever we had over here. So if the absolute value of the error is less than your integral bound, oh, and I also forgot to define integral bound, it's okay. Then that means you want the integral to sum. Int integral is equal to integral plus error. And then if it's not within that bound, we just want it to be equal to 0. Else integral is equal to 0. Great. Now we can write the actual I power component. So int I power is equal to, remember, ki times integral. Also forgot to define integral bound. Int integral bound, you can have it as a float if you want, but I just prefer having ints because there's no need for that accuracy most of the time in Vex. Alright, great. So now, as talked about earlier, the power that you're going to be assigning to the motor is the sum of the p and the I. So the overall power, int pi power, is equal to p power plus I power. Then what we're going to do is we're going to return pi power. So that's pretty much all there is to it. This is a functional PID for the most part. All you need to do is pretty much understand how to use it, and we'll get to that in a bit. Here's a really quick guide on how to tune PID. This generally works best for chassis and for the 18:1 motors if they are direct drive. So the general, just if I want to tune a PID real quick, the general convention is this. This is what I follow. So an error of 1000 times your kp should approximately be equal to your max millivolts for the motor, which is 12,000. So with this you get approximately a kp of 12. And then chances are I would need to increase that kp to some number. And then after finding the right kp, this is what will happen. So let's just say this is error on the y-axis, this is time on the x-axis. So then what I will see is I'll see some plateau, or I'll see some asymptote. This indicates to me that I found the correct kp for this tuning method. So kp check. Then afterwards, after finding the kp here, you can start the ki. The ki generally is like 0.1 times your kp as a good baseline, and then you just play around with that number until you see good accuracy. For lifts, it's a little bit different, but the idea of having a small baseline, then just adding up until you see that plateau, and then starting on the ki, that overall framework still applies for lifts, and pretty much any system that you're going to use for PID. So this example slide over here, it's pretty much a bit more complete example compared to whatever was previously shown. So as you can see, we're first defining the motor over here in port 3. It's right drive motor, we're just doing 1 for the sake of this example. And then we're first declaring all our variables. We have the constants up here, target, error, I bound, integral bound, and then integral. You can have these as local variables as well, just for this example one. They're global. It's preference. And then next we have the PID function over here, or the PI function. Your parameter sensor, so you're going to be entering in the encoder that you're trying to use the PID for. And then we have the standard. Line 11 we have error, line 12 we have P power, line 13 to 15 we have the integral component, line 16 and 17 we're just pretty much getting the power all together. And then in lines 19 and 20 we're checking if the power is beyond the max power that we set, and that's 12,000. If it is, we're just correcting it. Then line 21, we're returning the power. So then lines 10 to 21, it's pretty much just the function of the PID, and that's nothing new. Yeah. Then line 23, this is where the PID task is at. So we see inside this PID task, the power is being continuously calculated using the PID function. And then over here on line 26 as well, we see the motor being assigned to the power that was calculated by the PID function. Also, one quick thing to note, we're also entering in the sensor as the right drive encoder as the argument for the PID function, and that's just something to keep in mind. And then after applying power to that motor, within autonomous, this is a better idea of how exactly to implement this into your code. So we're first assigning the KP values and the KI values on 30 and 31. And then afterwards on line 32, we're starting the PID task. Then line 33, we're setting a target or where we want to go to. Then line 34, we're giving the motor some time to actually get to that target and then settle. And then on line 35, we're just stopping the PID task. Of course, after line 33, you can change the target as many times as you want, but this is just a brief example. Now we can move on to the logic for the straightening code. So for this type of straightening code, the overall straightening code that I'll be describing works this way. So what we're going to do is we're going to check the rate of each of the sides of the chassis. We're going to check the rate of the right side, and then we're going to check the rate of the left side. So let's give an example. For example, let's say that the right side moves 600 encoder units, and the left side moves 500. These both happen within the same specified time. As the right side traveled a greater distance in the same amount of time, that means that the right side probably has a bigger rate. What that means is that the chassis swerves off something like this. So it's not moving straight, in other words. So the straightening code that I'm about to describe pretty much adds a boost onto the left side, or it adds a boost onto the lagging side. The way to do this is that you will actually have a straightening power, and it's a P controller. Straightening power. Let me just write this. Yep. So you're going to have a P controller for your straightening power. The straightening power will be equal to your right encoder minus your left encoder times a straightening constant. You can have a full-on PID or PI controller for the straightening code as well, but if your chassis has good build quality and it's solid, a P controller should be enough. In most scenarios as well, a P controller is enough. So over here, as we can see, let's for example just say the KS is equal to 1. You're adding extra power over here that will be equal to approximately 100. And what that will do is just give the left side a little bit of boost so that the rates of both of the sides are the same and that the chassis moves straight. Now this is example straightening code on this slide. Lines 3 and 4 we are declaring the motor, and then from lines 6 through 12, all of that information was pretty much what was on the previous slide. This time is just condensed for the sake of the slide and so that everything can fit. The only difference lies within lines 27, 28, 29, 30, 31, and 32. In other words, the only difference is within the PID task itself. What's happening differently is that another way to actually straighten is to individually calculate the PID of each sides of the chassis. For example, in line 27, we're individually calculating the PID for the right side of the chassis. And then in line 28, we are individually calculating the PID for the left side of the chassis. So then, if this is not sufficient in order to straighten out the chassis, as for example, if the left side is lagging, due to the nature of PID, the left side will automatically receive a boost. The reason for this is because the error is bigger. However, if this is not sufficient, within line 29, we see that we are taking the difference between the encoders. And then in line 31, we're actually adding a certain power to the left side if that's still lagging. The power that we're adding is a constant times the change in the encoder, or the difference between the right encoder and the left encoder. It's pretty much whatever was discussed in the last segment. And then as we can see in line 34, the only difference from this method is that we have to both say the target for the left side and the right side this time. That's pretty much it. Everything else works the same. So overall, this is the information that was covered in this video. We talked about the built-in encoder rotate functions that are in VEX code. We talked about a PI controller, and then we talked about straightening code as well. Thank you for watching, and I'll see you guys next time.